I am Mrs. Rajakumari, Assistant Professor of Mathematics, RMD Engineering College. In this lecture, we learn how to evaluate integrals using Laplace transform techniques. Evaluate integral 0 to infinity e power minus t cos 2t dt. The above integral is same as integral 0 to infinity e power minus st f of t dt with f of t equal to cos 2t and s equal to 1. By comparing these two integrals, we see f of t is cos 2t and the coefficient of e power minus t is s value, which is 1. But integral 0 to infinity e power minus st f of t dt is the definition of Laplace transform of f of t. Therefore, integral 0 to infinity e power minus t cos 2t dt is equal to the Laplace transform of f of t cos 2t when s is equal to 1. That is, the Laplace transformation of cos 2t is s by s square plus 2 square when s takes the value 1. It is 1 by 1 plus 4. The answer is 1 by 5. Problem number 2. Evaluate this integral. That is, to evaluate integral 0 to infinity e power minus 3t t sin 2t dt. The above integral is same as integral 0 to infinity e power minus st f of t dt with f of t equal to t sin 2t and s equal to 3. But integral 0 to infinity e power minus st f of t dt is the Laplace transform of f of t. Therefore, integral 0 to infinity e power minus 3t t sin 2t dt is equal to the Laplace transform of t sin 2t with s is equal to 3. Now let us find the Laplace transform of t sin 2t. It is minus d by ds of the Laplace transform of sin 2t with s value as 3. It is equal to minus d by ds of the Laplace transformation of sin 2t is 2 by s square plus 2 square. Differentiation of this function, that is minus 1 by s square plus 4 into 2s. But s is equal to 3. It is 4s by s square plus 4 with s value to be 3. It is 4 into 3 plus 9 plus 4, 12 by 13. It is s square plus 4 the whole square. It is 12 by 169. Problem 3. Find the value of integral 0 to infinity e power minus t sin root 3t by t dt. The above integral is same as integral 0 to infinity e power minus st f of t dt with f of t equal to sin root 3t by t and s equal to 1. But integral 0 to infinity e power minus st f of t dt is the Laplace transform of f of t. Therefore, the given integral is equal to the Laplace transformation of f of t, where f of t is sin root 3t by t with s equal to 1. It is equal to the Laplace transformation of sin root 3t by t. Since it is division with t, we integrate the Laplace transformation of sin root 3t between s to infinity with respect to s. But s is equal to 1. Equal to integral s to infinity. The Laplace transformation of sin root 3t is root 3 by s square plus root 3 square ds. Integration of ds by s square plus a square is 1 by a tan inverse of s by a. It is tan inverse of s by root 3 between the limits s to infinity at s is equal to 1. On applying the upper limit, tan inverse of infinity, it is pi by 2, minus the lower limit is s, we get tan inverse of s by root 3 at s is equal to 1, equal to pi by 2 minus tan inverse of 1 by root 3, that is equal to pi by 2 minus tan inverse of 1 by root 3 is pi by 6. It is equal to pi by 3. Problem 4. Evaluate the integral 0 to infinity sin 2t by t dt. The above integral is same as integral 0 to infinity e power minus st f of t dt with f of t equal to sin 2t by t and s equal to 0 because there is no exponential function. But integral 0 to infinity e power minus st f of t dt is the Laplace transform of f of t. Therefore, integral 0 to infinity sin 2t by t dt is equal to the Laplace transform of sin 2t by t at s is equal to 0. It is equal to, since it is division by t, we have to integrate the Laplace transform of sin 2t with respect to s between the limits s to infinity at s is equal to 0. It is equal to integral s to infinity. The Laplace transform of sin 2t is 2 by s square plus 2 square ds at s is equal to 0. It is integral, it is 2 into integration of ds by s square plus a square is 1 by a tan inverse of s by a between s to infinity at s is equal to 0. On applying the upper limit, we have tan inverse of infinity pi by 2 minus the lower limit is s, we get tan inverse of s by 2 at s is equal to 0. It is pi by 2 minus tan inverse of s is 0 means it is tan inverse of 0. Tan inverse of 0 is 0. So the value of the integral is pi by 2. Therefore, integral 0 to infinity sin 2t by t dt is equal to pi by 2. Next problem. Prove that integral 0 to infinity e power minus at minus e power minus bt by t dt is equal to log b by a. The above integral is same as integral 0 to infinity e power minus st f of t dt with f of t as e power minus at minus e power minus bt by t and s is equal to 0. Therefore, integral 0 to infinity e power minus at minus e power minus bt by t dt is the Laplace transform of this function at s is equal to 0. Now let us compute the Laplace transform of e power minus at minus e power minus bt by t. Since this function is divided by t, it is the integration of the Laplace transform of e power minus at minus e power minus bt with respect to s between the limits s to infinity. It is equal to integral s to infinity. Laplace transform operator is a linear operator. So Laplace transformation of e power at given by 1 by s plus a minus the Laplace transform of e power minus bt. It is 1 by s plus b. We have to integrate this function with respect to s. s by s plus a, it is log s plus a minus integration of ds by s plus b is log s plus b between the limits s to infinity. It is log a minus log b can be written as log s plus a by s plus b between the limits s to infinity. We have to apply the upper limit for s as infinity. It can be written as limit s tends to infinity logarithm of s plus a by s plus b minus the lower limit is s. So we get log s plus a by s plus b. To apply the limit, take s common outside from the numerator. So it is log of s into 1 plus a by s divided by, take s from the denominator, it is 1 plus b by s minus log of s plus a by s plus b. S and s cancels. Now when s approaches to infinity, it becomes a by infinity. A by infinity is 0. Similarly here b by infinity, it becomes 0. It is log 1 minus log s plus a by s plus b. Log 1 value is 0. It is minus log of s plus a by s plus b. Let us substitute this value in equation number 1. Therefore, it becomes minus log of s plus a by s plus b at s is equal to 0. When s is 0, it is log a by b, which is same as log of b by a. Thus proved. Problem 6. Evaluate this integral by using Laplace transforms. By comparing this integral with the definition of Laplace transforms, we see that here f of t is equal to cos at minus cos bt by t and s is equal to 1. Therefore, the given integral is equivalent to the Laplace transform of cos at minus cos bt by t at s is equal to 1. So let us evaluate the Laplace transformation of this function and substitute in equation 1. Laplace transformation of cos at minus cos bt by t is equal to integral s to infinity the Laplace transformation of cos at minus cos bt. L is a linear operator, so I can write this as L of cos at minus L of cos bt is equal to integral s to infinity. The Laplace transformation of cos at is s by s square plus a square minus s by s square plus b square. We have to integrate this function with respect to s. To integrate this function, let us use the substitution method. Take t as or take x as s square plus a square. Therefore, dx is equal to 2s ds. Therefore, integral s by s square plus a square ds is equal to integral dx by 2 divided by x. It is 1 by 2 into logarithm of x. It is 1 by 2 log of s square plus a square. Therefore, the evaluation of the first integral gives 1 by 2 log of s square plus a square minus the evaluation of the second integral gives 1 by 2 log of s square plus b square between the limits s to infinity. It is 1 by 2 into log a minus log b can be written as log of s square plus a square by s square plus b square between the limits s to infinity. It is 1 by 2 into the upper limit is infinity. It is limit s tends to infinity log of s square plus a square by s square plus b square minus the lower limit is s. So we will be getting the same function log of s square plus a square by s square plus b square. which is equal to 1 by 2. It is limit s tends to infinity log, take s square common outside from the numerator as well as from the denominator. It is 1 by a square by s square divided by s square into 1 plus b square by s square minus log s square plus a square divided by s square plus b square. Cancelling s square and s square, and when s approaches to infinity, s square also approaches to infinity. So a square by infinity is 0. So numerator becomes log of 1 by 1. It is 1 by 2 log 1 minus log of s square plus a square divided by s square plus b square. Log 1 is 0. So we get the answer 1 by 2 log of s square plus b square divided by s square plus a square. Therefore, equation 1 becomes integral 0 to infinity e power minus t cos at minus cos bt by t dt is equal to the Laplace transformation of cos at minus cos bt by t. That is 1 by 2 log of s square plus b square by s square plus a square at s is equal to 1. It is 1 by 2 log of 1 plus b square by 1 plus a square. Then evaluate the integral 0 to infinity e power minus t sin square t by t dt. Comparing the given integral with the definition of Laplace transform, we see that f of t is sin square t by t with s is equal to 1. Therefore, the given integral is equal to the Laplace transform of sin square t by t when s is equal to 1. Let us evaluate the Laplace transform of sin square t by t. Since this function is divided by t, we use integral of transforms, where we integrate the Laplace transform of sin square t between the limits s to infinity with respect to s. And Laplace transform of sin square t is evaluated by giving a trigonometric substitution for sin square t as 1 minus cos 2t by 2. Taking this 1 by 2 common outside and applying the linearity property of Laplace transforms, we get 1 by 2 integral s to infinity Laplace transformation of 1 minus Laplace transformation of cos 2t, which has to be integrated with respect to s. And finally we substitute s is equal to 1. The Laplace transformation of 1 is 1 by s, and the Laplace transformation of cos 2t is s by s square plus 2 square. Now coming to the integration of this function, integral ds by s is log s, and integral of s by s square plus 4 with respect to s is given by the formula 1 by 2 log of s square plus a square. Here a is 2, so we get 1 by 2 log of s square plus 4, where the limits of s is from s to infinity. To simplify this function, let us multiply and divide by 2 to the first function. We get 1 by 2 into 2 log s. Now taking 1 by 2 common outside from the two terms, we have 1 by 4 into this 2 log s can be written as log s square by using the properties of logarithms minus log of s square plus 4 between the limits s to infinity. Now log a minus log b is equivalent to log a by b. So we have log s square by s square plus 4 between the limits s to infinity. On applying the upper limit for s as infinity, this function reduces to this term minus the lower limit is s, so that we have log of s square by s square plus 4 at s is equal to 1. When s approaches to infinity, this term reduces to 0, and we have 1 by 4 log of s square plus 4 by s square at s is equal to 1, which is equivalent to 1 by 4 log of 5. Problems for practice. Do complete these problems. Refer to the material on Laplace transforms, which is already sent to you. Work out the exercise problems given in the material The more and more you practice, you acquire confidence in the topic. Doubts are welcome. Thank you.